So, hi, good morning everybody. So, yeah, let's start with a recap of where we got to yesterday. So, we defined a few notions of general relativity that we are going to use to discuss this example of the Kerr-Newman black hole. So we introduced the electric charge and the magnetic charge. These I have not rewritten. Then I've discussed how to assign charges to the space-time symmetries. In particular, we considered the case where k, the Killing vector k, is always time-like, and we can choose in some appropriate system of coordinates that it is proportional, or it is d over dt. And we define the Komar mass, as you see above. And similarly, for the case where there is a Killing vector that is space-like, it generates a U1 isometry, we defined a Komar angular momentum. So this will be, for this course, this will be our definitions of mass and angular momentum. There are alternative definitions, and these lead to different notions of mass, for instance, that sometimes agree, most of the times agree with this, but not always. And we also demonstrated this generalized SMAR relation for a rotating space, axisymmetric and stationary space-time, and we saw the appearance of the area of the horizon there. Kappa was the surface gravity, and here xi is the Killing vector that we say generates the horizon. Anyway, it's the Killing vector that becomes null at the horizon. And we recall the fact that the horizon is the event horizon is most of the times, and anyway, it will be true in this case, a Killing horizon, meaning that there is a null, the horizon is a null hypersurface where this Killing vector becomes null. And yesterday, when I discussed the surface gravity, when I had some confusion that I would like to clarify. So we had this hypersurface that was our null hypersurface, and there was the normal Killing vector xi. So this was the Killing horizon. And we said xi dot xi. By the way, by xi dot xi, just to clarify the notation, I mean just the contraction of the indices. Xi dot xi is null on n. And then I say something confusing about this gradient. I said that this is proportional to xi, but I didn't really motivate well why. So the fact is that xi dot xi is 0 everywhere on n. So as long as I move tangentially to n, xi dot xi, this function xi dot xi, the square norm of xi, is 0 on n. So the gradient along the surface, the part of the gradient that is tangent to the surface, is just 0. So the only non-zero part of this gradient is when I move orthogonally to the hypersurface. So this part can only have is only non-zero if I move out of the hypersurface, and the normal vector is xi. There is just one normal vector because it's a codimension 1 hypersurface. So the normal to the hypersurface is proportional to xi. So this was the starting point for showing the formula for the surface gravity. Is this okay? It was just a small remark. Another small remark is that the notes will be available soon, maybe today, or maybe they're already available. I don't think so, but they will be put on the website soon for the first 3 lectures at least. And so there you find all the demonstrations that I did, and also the references that I'm just mentioning. Wald's book, Carroll's book, sometimes some other references. You will find the precise references in the notes, so I don't need to write them all the time. Okay, So then we started discussing the Kerr-Newman solution. It's a solution to the Einstein-Maxwell theory in 4 dimensions. And it has this form. The matrix is here. Here is the form of the gauge field. Here are the functions that appear there. And then we had the parameters M, A, Q, and P. And I claimed that if I measure M comma, I get precisely M. And if I measure J comma, I get A times M. Okay, let me also, it will be important, it will be more clear in a second, but maybe you already see this, to check what are the zeros of this polynomial. So this delta is depends on the parameters M, P, Q, and A. P and Q are associated with electric and magnetic. Q is the electric and P is the magnetic charge. And it is a function of R. It's a quadratic polynomial in R, so it can possibly have 2 zeros. So we can write it as the solutions to, we can write first delta is R minus R plus times R minus R minus. So these are the roots of this. Oh, hi. Okay. So if I solve for, if I just look at the roots of this polynomial, I just find these expressions. This will be useful in a second. Sometimes for the records, I will use this later on. We also need these relations that just follow from above. So the sum is 2m and the product is this. And I made the remarks that I can take some limits of this solution, and they give us more familiar solutions. Like if I take, I cannot take m equals 0, otherwise the horizon is washed away. But I can take a to 0, so they switch off the rotation, and I'm left with the Reissner-Nordstrom black hole with electric charge Q and magnetic charge P. Or I can set Q and P to 0, and then I'm left with Kerr. So this is the general metric. If you do this, you will recover maybe more familiar expressions for these Reissner-Nordstrom or Kerr black holes in the Boyer-Lindquist coordinates that are these ones. So now let's start analyzing where the horizon is and what happens asymptotically. First, we can check what is the asymptotic metric. So for R, the radial coordinate, very large. So as R goes to infinity, so one just has to remember that delta goes like R squared and sigma goes like R squared as well. Here is sigma, this function. And so for large R, we can approximate delta and sigma in this way. So the metric is really the one of Minkowski, so asymptotically. Sorry. So asymptotically, the space-time is flat. And this helps us in fixing the range of the coordinates, at least of these angular coordinates. Then we take theta between 0 and pi, so that this describes the two sphere that is in Minkowski space-time, and phi is identified up to 2 pi. Okay, and T and R are not restricted so far. And we also see that the vector K is d over dt is indeed a killing vector, is a killing vector of the full metric, because you see the functions don't depend on T and don't depend on phi, so phi is also a killing vector. And it is time-like. Asymptotically, it is time-like. K tilde asymptotically space-like. So we can use them to define our mass and angular momentum. And this is the first observation. So I would invite you to check this, the fact that the Komar mass and Komar angular momentum are those ones. Maybe even to check that this is a solution of the Einstein equations. It's some training that you can do with Mathematica quite easily. If you want, again, we can discuss this or compare what we get. I thought having a sort of Mathematica session on this, but then I thought it's maybe too trivial. So, but I'm happy to discuss whatever you find. Okay, now let's do something a bit less trivial. We start from infinity and we move along the radial coordinate towards the interior of the space-time. Of course, something strange happens at the zeros of delta, right? Because this part of the metric blows up. In Schwarzschild, this happens at the same time when the dt squared term vanishes. Here it's not exactly the same. This is because the killing generator of the horizon is not d over dt, but is a combination of d over dt and d over d phi. And let's see that. So we move from infinity towards lower values of r. We identify this locus delta equals 0, which is special. And in order to understand better what happens, let's just look at the part of the matrix that is that contains the time and radial differential, so the dt squared, dr squared term, and no, sorry, the dt and d phi squared. So let's take g to d. So I decide that I'm at delta equals 0 or close to that, and so I can fix r. I can fix the theta coordinate, and then I look at what remains. This is what remains. And let's analyze this matrix. So the determinant of g to d is, well, g t t, g phi phi, minus g t phi squared. And as long as this is less than 0, the matrix is non-degenerate and Lorentzian. This doesn't necessarily mean that GTT is negative, but, well, there is a positive and a negative eigenvalue, so the matrix is Lorentzian. The explicit form of g phi phi, gt phi, and gtt can be read by comparing these two expressions. I'm not writing them again. It's just, and they are not mysterious functions. They are those that appear over there. Okay. So the null hypersurface that is so we have a null hypersurface that is this one, G, when the determinant, and that is what I just wrote above, vanishes, when then the metric is no more Lorentzian, so I have a null hypersurface there. So let's see more precisely this. This may be, I can erase this. Let's go. So if you compare, I'm not really to go through all details, but if you compare the GTT, G55 expressions with the ones that are written here, you can see that this determinant of G2D is minus delta times sigma times sin squared of theta. So as long as, so sigma is always non-vanishing, sin squared theta apart from theta 0 and pi is non-vanishing. So as long as delta is non-zero, this matrix is indeed non-degenerate and Lorentzian, but when delta is 0, I have something particular. This we already saw, at least in these coordinates. And so it is when delta equals 0 that this null hypersurface appears. And delta becomes 0 when R is equal to R plus or R minus. So in these positions we have null hypersurfaces. So I'm not going through all the details, maybe you already saw these things, at least for Schwarzschild. These, one can see that these are actually just coordinate singularities, they are not really curvature singularities, and one can change coordinates, extend the space-time, so introduce critical coordinates, and see that these locus, these null hypersurfaces are perfectly regular and fine. On the other hand, there is a curvature singularity if you compute the Riemann tensor and the Riemann squared. So far we have found a null hypersurface, and I will show that there is a killing killing vector, that becomes null there. And on the other hand, we also find a curvature singularity in sigma equals 0. This can be seen by computing the square of the Riemann tensor. For instance, this is called a ring singularity. If you're familiar with Kerr, you find a ring singularity, something that has the shape of the ring, sometimes also called the ringularity, because it's a ring singularity. Okay, but to make the connection with what we have seen so far regarding killing vectors, let's look for this killing vector that is null on the hypersurface that we have identified on R plus or R minus. We will be mostly focused on R plus, that is the outer horizon, R minus is the inner horizon. So I guess I can erase this. So I said in general, the killing vector that is null, well, first of all, it is not just dt, del t, because you see that the norm of del t is a function here, and when delta is 0, this does not vanish, so certainly it's not del t. But we said in general, it will be a combination of del t and del phi, and this constant needs to be determined. It's what we are going to do now. And this, we expect this is a constant, because otherwise it would not be obvious that this is a killing vector if these two are killing vectors. So let's study this. I claim that omega h given by minus g t phi over g phi phi evaluated in R plus. Let's focus on R plus. The same things can be done for R minus, but we will focus on R plus, the outer horizon, the first that we encounter when we move from larger values of R. So if you do this, you will find that this is A over R plus squared plus A squared. How do we see that? So let's look. What is GT phi? GT phi is this. I have to evaluate this at delta equals 0. So you see I have R squared plus A squared over sigma times sin squared theta. But I have to divide this by G phi phi. G phi phi is this. At delta equals 0, also have r squared plus a squared, but it's squared, so I get this term over there. Then I have sigma, and here I had this 2a that correspond to this a here. So I think everything works out. If there is any doubt, just let me know. It's just comparing.
Have you evaluated that formula for R minus? Have we obtained the same or not?
So for R minus, you can evaluate it in the same way. You will get exactly the same with the minus here.
Yeah, but I thought we said that omega h was constant.
Yes, omega h is constant on the horizon, but here we have two horizons, we have two omega h's. I should have introduced omega plus and omega minus. Omega plus is the angular velocity of the outer horizon, minus for the inner horizon. But since we are only going to discuss the outer horizon, I call this omega h, and I just use r plus here. But the same thing can be done for r minus. So far there is no difference, at least in these concrete computations between the two. So this is just a claim. I just claim that this is the correct angular velocity to stick here. So let's check that this vector xi is indeed null at the horizon. So we compute xi dot xi. So I will have gtt from this part of the matrix. Then I have plus 2 times g t phi times omega h plus g phi phi omega h squared. This is just the norm of the vector. Just ask if anything is confusing. But now, since I chose on my omega h in a wise way, I get gtt plus, or better, minus 2g t phi squared over g phi phi plus g phi phi, no, sorry, gt phi, g. Yes, I'm just replacing my definition of omega h in here. And so you see this is the determinant of g2d divided by g phi phi. I gave the expression of the determinant over here, so it's just this. So it is 0 when evaluated in R plus. So when I evaluate my killing vector, the norm, square norm of the killing vector in R plus, I indeed find that it is 0. This is because we have chosen omega, the coefficient of this combination, in the correct way. Okay, so this you can do, I applied this to the Kerr-Newman solution, but you can do the same procedure in other rotating black holes in different dimensions. In ADS, it works in the same way. This is a way to find the angular velocity. So this somehow let's try to remember this expression, or I'll write it maybe again. This is the angular velocity of the Kerr-Newman black hole. This is the angular velocity of the horizon. It's controlled by A, which is meaningful because we said before, I just claimed that when I switch off A, I switch off the rotation, the angular momentum, and correspondingly I switch off the angular velocity. It makes sense. Say it again.
When A is large, you also switch off omega. What is the intuition?
When A is large.
Switches off omega. It goes to 0 when A goes to 0, and it goes to 0 when A goes to infinity as well.
Yeah, there is a limit. Physically, there is a limit in taking A arbitrarily large.
Yeah, I mean, R plus would be defined, right?
R plus would not be well defined, yes, because R plus contains square root of minus A squared. Yes, there is a limit indeed. Actually, let me make this comment here. I will come back later. There is also a limit. So one would say, okay, I cannot go beyond extremality. Extremality is when the square root, so I have R plus and R minus, and there was a square root appearing there. When this square root vanishes, I have extremality. But one can also see that physically, in an astrophysical context, it's also very, very hard to reach extremality. So this corresponds to the third law of black hole thermodynamics that we will see in a second. So it's very hard to reach zero temperature. So there may be problems even before you reach this extremal value of A. Okay, so far good. So related to what I just said, for now, we will always assume, or actually always, we will always assume that m squared is larger or equal than a squared plus b squared plus q squared, and that m is larger than 0. This guarantees that r plus and r minus are real and positive. So they appear before the singularity that is close to r equals 0, let's say. It was at sigma equals 0, the singularity. So, okay, we make this assumption, and the extremal value of the black hole that will become important later on is when I have this bound is saturated. So this, if you remember the expressions of R plus and minus, we ensure this. If the singularity is not screened by the horizon, we say we have a naked singularity. This is considered non-physical, so we don't want to study that situation. Then we had introduced the surface gravity. So let's see. Here, this I cannot really compute at the board. I'll give you the result, but then we will use it. So kappa is r plus minus r minus over 2 a squared plus r plus squared. So kappa is this surface gravity. So we notice, this again will be important when we discuss the extremal case, that there is a situation when the two horizons merge, when the surface gravity vanishes. So r plus is equal to r minus, again, when the square root that I've now erased so recall again, r plus r minus was m plus r minus square root. When this square root vanishes, the two horizons merge, and then we have that the surface gravity also vanishes. And also, it's not hard to measure the area of the event horizon. So it will be the area of some sphere, but we have to take the sphere that is at r plus. So since it's the area of the sphere, I have to integrate over d theta between 0 and pi, integrate over d phi between 0 and 2 pi, of the square root of g theta theta g phi phi in r plus. So if you now go and search for g theta theta g phi phi, you evaluate it and take the square root, there will be some sine of theta, and I have to evaluate this at delta equals 0. So all in all, you get 4 pi, and then there is the function r squared plus a squared evaluated in r plus, so it's this. Okay. I copy there the angular velocity as well. Omega h is a over r plus squared plus a squared. Now we want to check the smart relation. So we have found omega, we have found the area, we have found surface gravity, the mass is m, the angular momentum is a times m, and so we want to check this smart relation. Here, let me do this by switching off the charge. So that we don't have the extra contribution from the electric charge. So since we have found kappa and we have found A, we can see that the product kappa times A is r plus minus r minus over 2 is the same as r plus minus m. Let's keep it there. And also we can compute 2 omega j. This is 2a squared m. So here I'm computing the ingredients that enter in the smart relation. So we have kappa times A, we have omega times J. It's this expression. I'm just replacing the expression for omega and the fact that J is A times M. So here it is. Then we somehow manipulate this, recalling that we are at R plus, so at R plus in R equal R plus, delta is 0, so we can use the fact that r squared plus a squared is 2m r plus. This comes from the definition of delta over there when I set q equal p equals 0. So now in the smart relation we had kappa times a over 4 pi plus 2 omega h j. So I add up these two with the appropriate coefficients. The 1 over 4 pi here. Sorry, I probably forgot the 4 pi here. There it is. R plus squared minus m r plus a squared over r plus. And this is, what is this? Just use this. Yes, it's the mass. You look at this, just replace this, and you find m. And we have verified the smart relation. Not surprising, it had to work, but it's nice to verify this in detail. So as an exercise, you could repeat the same thing, but adding again the electrostatic potential. So take Q different from 0 and P equals 0. And you will find that phi h that I defined yesterday. So yesterday I defined phi h as xi dot a in at the horizon, in our case in R plus. So I define this. You find that this is q r plus over r plus squared plus a squared. So again, it is controlled by q. If q is 0, the potential, electrostatic potential goes to 0. And once you have found this, you can check the smart relation, including the contribution from the electromagnetic field. And so we have somehow this solution a bit better under control. We have computed the charges, verified the relation, computed the area, the surface gravity, and we will use it again later on. So is there any question about this example? Yes?
Why is R minus not a horizon?
R minus is another horizon. Just
So why didn't we do this calculation?
you can do that. You can do that as well.
Does that mean that we have to assign two angular velocities to
Yeah, yeah.
areas?
Yeah, but we will just study the horizon that is the event horizon. The inner horizon is a Cauchy, called the Cauchy horizon. But for the physics that is outside, that is connected to the asymptotic region. So if this was Schwarzschild, okay, let me not draw the Penrose diagram for this, but for the physics that is connected to infinity, the relevant horizon is R plus, because it's the outer one.
And the surface gravity, does the R minus just pop out of the outer, or do we have to actually use the inner?
You would need to evaluate, so the formula for the surface gravity is the same. So kappa squared was minus a half d mu xi nu d mu xi nu evaluated at the horizon, so you would need to evaluate this in R minus instead of R plus. The formula is the same, but you need to evaluate it in R minus.
So that is specifically for R plus.
This is the one, yes. I should always write K plus, A plus, but I just declared, I just look at the outer horizon. The area as well would change. Are there other questions about this example? Yeah, just one second.
What's inside the singularity?
No, we are not reaching the singularity. We are not reaching the singularity here. We have the singularity, somehow the singularity, the inner horizon, the outer horizon, and the infinity. So the issue with the inner horizon is that it can see the singularity. If you are in between the inner horizon and the singularity, you see the singularity. But we are not going to discuss anything inside the horizon. We are not going to discuss in these lectures.
Yesterday we said that the surface gravity was related to the temperature.
Yeah.
So when the square root vanishes, does that mean the temperature vanishes?
Yeah, exactly. So the question is what happens when the surface gravity vanishes. So I said, and we'll motivate more in a second, that the temperature would vanish. And indeed, we say that for extremal black holes, the temperature vanishes. And it's what defines the extremal black holes. Okay, if there are no more questions about this example, I would start introducing black hole thermodynamics more systematically. So far I just made some comments here and there, but now let's see this more in detail. So for these 10 minutes, maybe I'll make some heuristic comments. So far we have seen no hint of thermodynamics, why there should be a thermodynamics associated with black holes. Well, the first question that was asked apparently by Wheeler to his student Bekenstein was the following. Not this, but let me first. So this is a new chapter of the lectures. So the question that apparently Wheeler asked to Bekenstein, and then Bekenstein elaborated on, is what happens if I throw a cup of tea in a black hole? A cup of tea is something that carries some entropy, it could be a book, something else. and I throw it into the black hole, and the entropy seems to disappear because nothing comes out, is lost forever. And this is disturbing because the second law of thermodynamics is not something that we would like to violate, usually. So the question was very, very simple, just this. So the idea is that maybe black holes carry entropy, so that somehow if you throw something that has an entropy in the black hole, the entropy of the black hole increases, and the overall entropy does not decrease. So the second law is satisfied. Moreover, black holes are formed by matter, the collapse of matter, and this for sure carries entropy. So it would seem that you have matter with an entropy, a lot of matter, then collapses from the black hole, and suddenly the entropy has disappeared. This is also disturbing. So these two are just two ways of saying the same thing, that the entropy should not be lost inside the black hole. And let's see something slightly more quantitative. It's just an heuristic argument, but let's make it anyway. So suppose that we have a Schwarzschild black hole, and to throw some quanta of information, some classical bits of information. Could be also some spin up and down if we want to do some quantum mechanical. So if we have n of them, n bits of information, whatever it is, it's not important. The number of states that is associated with this object is growing exponentially in n. If this were spin up and down, it would be 2 to the n. No? So it's exponentially in n. So say number of states is, let me just write roughly. We want to make some rough argument only, e to the n. So the entropy, S, that is log of the number of states, will be proportional to n. So now this quanta of information, these bits of information, in order to fit into the black hole, must have a size that should not be larger than the Schwarzschild radius. So far I've spoken about the Kerr-Newman solution. There was R plus, R minus, but when we set A equal Q equals 0 and P equals 0 so that we recover Schwarzschild, we have just one horizon. It's the one you're probably used to. So let me call this RS is the Schwarzschild horizon. Schwarzschild radius of the horizon. This is proportional to m, is g times m. There is, forget the factors of 2. Okay, so this, our quantum must be of a radius that is at most the one of Schwarzschild, otherwise somehow it doesn't fit. So the energy must be at least, the energy must be larger than 1 over Rs. So now, so since the radius is, since the size is R, the energy is 1 over the typical energy associated with this, let me call it quantum of information, is 1 over the size. The scale, the only scale I have is this Rs, so the energy is at least that. Since the size is less than R, then the rest is large. The energy I can associate this to this object. Don't take this too seriously. It's just some argument that somehow works. So the change in entropy when I throw my quantum information in the black hole, the entropy changes, possibly. Is the variation, the differential of the entropy, is the variation is proportional to the number of states. so the variation in the number of states. So this would be the number of quanta, sorry. The number of states changes, of course, but here I'm looking at the variation of the entropy, which is the logarithm of the number of states, so it's the variation of the number of quanta that I'm throwing in. So I'm adding quanta to the black hole. So I can convert the number of quanta into the variation in the number of quanta into the variation of the total energy by recalling that each of them has at least this energy. So this is a rough estimate, of course. And now I use the fact that the mass is related to the Schwarzschild radius, so I get something like Rs, dRs, because the mass and the Schwarzschild radius are proportional, over G. And this is like d of the area over G, because d of r squared is the d of the area. The area goes like r squared. So this is a very heuristic estimate, but it's inspiring, let's say, because it relates this theory of information here in a very crude, down-to-earth way to the variation of the entropy, which is somehow the core of Bekenstein's intuition. So the argument here says that the variation of the area is related to the variation of the entropy. So this is another motivation for associating some entropy to the black holes, and also to associate the entropy to the horizon area. Another point of view is that there are many ways to form a black hole, because I can collapse different stars, different types of gas, and in the end they end up in roughly, it seems, the same state, because the black hole is completely characterized, at least in classical GR, by the mass, the angular momentum, by the charges that I introduced before. They completely characterize the solution. They are the only parameters in the solution, as we saw for Kerr-Newman. There are no other hair on the black hole. So since there are many ways to form the black hole, maybe there is an entropy that is associated to the many different ways in which we can form the same macro state that is the same black hole. So enumerating these micro states, these many different ways to form the black hole, maybe gives the entropy. These are just thoughts, let's say. But now we will try to align this reasoning into the laws of black hole mechanics, make the laws of black hole thermodynamics. But maybe we can have the break now, and I will do this just later on. Okay, let's have a 10 minutes break or so. Okay, let's start again. I've been asked to clarify a bit these steps here, so let me come back to this argument for just a second. There was a step here, I was saying this is the number of quanta, let's call it that, that I throw in, and then I related this to this expression. Why? Because the number of quanta is the total energy, so it's M, the total energy of the black hole. So I'm increasing the energy of the black hole by throwing quanta in. So the number of quanta that fall into the black hole, N, is the total energy that I'm considering. Suppose I'm forming the black hole by throwing quanta, divided by the energy of a single quantum, and the single quantum had an energy that was at least over Rs, so this, we say this Rs times M, and this is what I used here. Is this clear? Hopefully. All right, so motivated by these arguments, let's formulate the laws of black hole thermodynamics. Actually, I should call them the laws of black hole mechanics. I call them the laws of black hole mechanics. They arise in GR, and then we compare them with thermodynamics. So the most suggestive one is second law, is really the central law. The first law is conservation of energy. It's also important, but the second law is really what characterizes thermodynamics. And it says, so now we formulate the second law, black hole mechanics. We give it a name, and then we compare, of course, with the second law of black hole of thermodynamics. So in any physical process, in any the area of the event horizon what does it do? Yeah, does not decrease. So this you can show in general relativity. There is no other extra argument of the type I made above. This is a theorem that you can prove, at least Hawking proved that. Is the celebrated area theorem by Hawking, that in any physical process, the area of the event horizon does not decrease. So it's a fact. It assumes, there are some assumptions, as always in a theorem. You assume cosmic censorship, and if there is matter outside the horizon, it should satisfy the weak energy condition. And I'm not going to prove this at all. If you want to find the proof, for instance, you can find it in Wald's book on general relativity. And this work by Hawking was also, there was some previous work related to Penrose energy extraction processes. So if you are familiar with that process, it's a process that you can affect a phenomenon that happens in the Kerr black hole, thanks to particular properties of the Kerr black hole, that by throwing particles in, you can extract energy. So you can increase the energy of the particle, you can extract energy from the black hole. So the mass can decrease. The mass of the black hole can decrease. You can take the energy out. But Christodoulou, before Hawking, showed that there is another quantity that he called irreducible mass that cannot decrease. And this irreducible mass is proportional to the square root of the area. This you can see. So this was realized in these kind of processes of the type of Penrose processes. And then Hawking showed this much more generally. So there is this quantity, the area that does not decrease in physical processes. So this inspired Bekenstein in the early 70s, 72, 73, to somehow associate an entropy to black holes, motivated by the previous arguments, and to relate the entropy to the area. Strictly speaking, the entropy could be a monotonic function of the area. If the area increases, and this monotonic function increases as well, so it would satisfy the second law. But the most naive and simple assumption is that there is an entropy, it's proportional to the area, and therefore the second law of thermodynamics would be immediately satisfied. And now, by discussing the first law, we see that this assumption is indeed a good one. I mean, in principle, it could also be, I don't know, something like a squared or something like this. But just from the second law we couldn't say, but we can test the other laws of thermodynamics and try to take these correspondence more and more seriously. But one thing we can immediately say is that whatever function of the area the entropy is, the dimensions don't match. So I have to divide this by something, and there is no scale in general, apart for the radius of the horizon that I'm using here in computing the area. There is no other quantity I can use, so I have to use some fundamental constants of nature, and Bekenstein introduced here the Planck length was known, but I used the Planck length there to define a dimensionless quantity that is the entropy. Here, okay, to be rigorous, I should say, let me set the Boltzmann constant to 1. There would be a Boltzmann constant here. Okay, so this dimensionless entropy is really obtained only if p squared here. This I'm emphasizing, p contains h bar, so sometimes you're taking in by hand h bar. The GR is telling you that there is an h bar, of course. There is no h bar in GR. But to make sense of this relation, to make sense of a relation between the area and some entropy that you want to make at this point, you need to introduce LP, and then there is h bar, and then something must be quantum. So this somehow helped in clarifying, in saving the second law, because it says that if I throw stuff into a black hole, the entropy does not really disappear, but it goes into increasing the area. Okay, but I could still decrease the entropy of the outer region by throwing stuff into the black hole. So it must be that the actual second law of thermodynamics, the ordinary one, gets generalized by including the entropy of the black holes. So there is a Bekenstein also formulated a generalized second law. Stating that the sum of ordinary entropy by ordinary entropy, I mean the entropy outside the black hole, and the black hole entropy does not decrease. And this has been checked in several examples, non-trivial examples. Okay, so this is as far as the second law is concerned. So we are going to test again this fact that the entropy should be really proportional to the area using the first law. But before, let's take an easy step and formulate the zeroth law. This we already discussed yesterday. So yesterday I didn't really prove the fact that the surface gravity is constant over a Killing horizon. I made the claim. We showed that this is constant on orbits of the Killing vector Xi. But okay, this is a fact. Again, it's a property of general relativity, something that you can demonstrate in general relativity. And now we want to make the connection with thermodynamics. And so this is parallel to the zeroth law of thermodynamics that says that the temperature at equilibrium is a constant of our thermal ensemble. Is constant over the ensemble. And So again, inspired by this, we make a connection between the surface gravity and the temperature. So again, it could be an arbitrary function. The surface gravity and the temperature could be related by some function, but the easiest and simplest thing to say is that the surface gravity is proportional to some temperature. This in GR by itself makes no sense. That's why originally these ideas were not really considered too seriously, at least, because the black holes in GR don't radiate. They don't emit anything. So what's the meaning of assigning a temperature? So it's just a formal thing. So as I said yesterday, there is a paper by Bardeen, Carter, and Hawking that is called the laws of black hole mechanics. They formulate these laws in this way, make the parallel with thermodynamics, but don't take it too seriously. So this was true until when Hawking himself, 2 years later, in 1975, proved that there is an actual emission of particles. So thermodynamics makes really sense. Let's come to the first law. So first law is basically conservation of energy. And in ordinary thermodynamics, we can express it in this way. If we have a variation of the energy of the system, it is related to a variation of the entropy plus the work that we do on the system. So this is the ordinary first law of thermodynamics. So if the system rotates, if we have an angular velocity omega and an electric so if the system is at angular velocity omega and it raised to the electric potential phi, so we do some work on the system by this, and we can write this same law in this situation as T ds plus omega dj plus phi dq. Okay, so this is the first law of thermodynamics in ordinary systems. We would like to see if something similar holds for black holes. We need to consider, if we want to test this in general, we need to consider a black hole that has an angular momentum, a charge, a non-zero area. This is the Kerr-Newman solution, for instance. So let's formulate the first law of black hole mechanics. I'll write it down. Well, first I read it, then I write it down. Let me just read it. If suppose there is a stationary black hole of mass m, angular momentum j, and electric charge q, we can perturb it a little bit. We want to obtain a variation of these charges. So we perturb it a little bit in some way, so that it settles down to a new solution, again a solution to the same system of equations that has a different mass now, different different angular momentum and a different charge. And therefore, we want to see if something like this is satisfied in this step. So I'll write it down. If So if we have a stationary black hole of mass m, angular momentum j, and charge q is perturbed. So that it settles down. To another to another black hole with mass n, let's say, plus dm, angular momentum j plus dj, and charge q plus dq, then the variation in the mass must be related to the variation in angular momentum and charge, but there's also a contribution from the variation of the area. Where the potentials that appear here are precisely those associated with the horizon that we introduced before. So if now we are going to prove this, at least in some context, but let's immediately compare this. So this is again a true law of general relativity. Again, I would like to emphasize that you don't get h bar or the Boltzmann constant here. Is not as direct as this. General relativity does not contain these constants. What you get is the product kappa times the A that is clearly to be compared with this T times ds. But there is no LP, Planck length, appearing. I will comment on this later on a bit more. But the LP squared, the fact that we divide by LP squared and multiply this other one by LP squared is done by hand. So what we can infer is that we can compare, when we compare this with that, we have kappa over 8, let me see, T ds is kappa over 8 pi dA. So from this, we would say that T must be kappa over 8 pi times some constant, alpha. We don't know what's this numerical constant. And A is the area, sorry, S is the area over alpha. And we don't know what this alpha is, some numerical constant. Here I'm setting the physical units to 1. The LP is 1 here. So this constant is not determined by this argument, but we can say that if this is true, the temperature must be really proportional to the surface gravity. It's not the square or the cube, or it's just proportional to the square for surface gravity, and similarly the entropy is proportional to the area. Okay, let's sketch a proof of this first law in the context of GR. It's just a sketch of a proof. And I will do this for the Kerr black hole. So I set the charge to 0. So there are uniqueness theorems for the Kerr black hole. And these uniqueness theorems say that the mass can only be a function of the area and the angular momentum. Or let me say differently, the area can only be a function of the only two parameters that can be there, and one is the mass and the other one is the angular momentum. So let me state this. So uniqueness theorems say, let me turn it in this way, that M can only be a function of the area and of J. Now in natural units, again we are using natural units, both the area and the angular momentum have the dimension of a mass squared. So the dimension of the area and the dimension of J is sorry, mass minus 2, I would say. No, it's not square. And then, okay, so just a second, the function m of a and j must be homogeneous of degree a half. Yes, of dimensional analysis. I'm just confused by the sign here. They must be homogeneous of degree 1/2. Sorry? So let's see.
When you use g equals to 1, isn't it that the sparsity that I use is equal to the mass of the black hole? So
Yes. It's plus. You're right. Sorry. Yes. I was confused by the fact that the area is yes, is a length squared. Yes. Okay. So thanks. So using this, we can now use Euler's theorem for homogeneous functions to say that the area times the derivative of the mass with respect to the area plus the angular momentum times the derivative of the mass with respect to j is 1/2 m. So this is Euler's theorem for homogeneous functions. This 1/2 is the degree of homogeneity. Okay. And now we use the Smart relation that we derived and we demonstrated it's true in general. We checked it for Kerr-Newman, but we derived it more in general. So this is a general relation that we can use here. So now let's compare what we have got here with this and rearrange a bit. So we have area times dm over dA minus kappa over 8 pi here plus j dm over dj minus omega h. This must be 0. Okay, but in general, I have two free parameters in this solution. In this, say, suppose it's Kerr, I can declare that these parameters are the angular momentum J and the area A. I have two parameters. I can trade one for the other. Let's say these two are J and A. So these two relations must be independent because I have two free parameters I can play with. So this relation and this other relation must be independent. So I obtain that dm over dA is kappa over 8 pi and dm over dj is omega. And this proves the first law when I have a zero charge, right? Because dm over dA is kappa over 8 pi, dm over dj is omega. And this I'm not considering in this argument. So this is just a quick sketch of the proof in this case when there is no charge. So you can check that the first law, this one, is satisfied by the Kerr-Newman solution. You can take really this expression and vary the mass, vary the area. So when you vary the area, you use the chain rule, you vary the parameters inside the area, and you do all this, you can check that it holds. When you have a concrete solution, a concrete black hole solution, it's also a way to extract the mass, another way to extract the mass of the solution. You impose the first law, you write it down. Once you believe it is satisfied, you write it down, and then you realize the non-trivial thing that all this combination is an exact differential, so it's non-trivial, so it's the fact that the first law holds. This is an exact differential, you integrate it and you get the mass. It's an alternative way to obtain the mass that is often used. I have in mind papers by Gibbons, Pope, Cvetic. Well, first, smart relation is not always satisfied. Now, in the case we have discussed, it is. For instance, in ADS, black holes is not satisfied. So this is, it is true that if I have the smart relation, okay, I just obtain the mass in this way. But sometimes I cannot use that, and I have to do something else. But the first law we expect, once we use all the variables, we include all the terms, that should be satisfied. Again, as I said, it's the definition of mass in GR is a bit delicate, or there are different notions. In asymptotically flat or asymptotically ADS spaces, the definitions may not always work in the same way. So it's a posteriori check that you have to make. For instance, I can define my mass by integrating the first law here. I have an expression. I can define the mass where it is well defined using the Komar integral. In the asymptotically flat case, I obtain another expression, and then I have to compare and see. And in this case, it's always true that they agree. But a priori, in different situations, you may have to check. There are general results anyway, that there is agreement when both are well defined. Okay, so we just need to discuss a little bit the third law. I've written down the second law, generalized second law, then the zeroth law, the first law over there. So I can erase this proof of the first law. For the third law, I don't really want to write down anything apart that it exists. Because it is on less firm grounds. So one formulation in ordinary thermodynamics, one formulation of the third law is that it is impossible to reach zero temperature by a finite number of steps in a physical process. Another formulation says that the entropy must vanish at zero temperature. So, but this is not true in general. It's not true even in ordinary thermodynamics, because you may have a system that at zero temperature is made by more than one state. It has more than one ground state, so the entropy is not strictly zero. It will be small, maybe, but not zero. And the true is for black holes, because we discussed this case of extremal black holes. You can see that if you take your Kerr-Newman solution, you impose extremality, that is the surface gravity, that is the temperature vanishes. So this is this. You impose this. You have a relation between the parameters, is what makes m equal square root of p squared plus q squared plus a squared. This is the extremality limit. And you can check that in this case the area is not zero. In this case the area is not zero. So certainly the entropy does not vanish in general for extremal black holes. So this version of the third law is not true in black hole thermodynamics. But it makes more sense to say that it is impossible to reach zero temperature by a finite number of physical processes, because this is what I alluded at before. It has been, explicit computation for realistic Kerr black holes in astrophysics show that it becomes harder and harder to increase the angular momentum of the black hole so that it approaches extremality one step after the other. Suppose you do this in different steps, and it becomes harder and harder to do that. So it's very hard to reach extremality. So one may even say that extremal black holes are just some ideal toy model, but don't exist, strictly speaking. Okay, anyway, this is, I don't want to write anything about that more than that. But this will be important later. These extremal black holes that maybe don't exist will play a role for us because they are nice, because they are at 0 temperature, so they are more simple. We just, if we ask what's the entropy of a black hole, we have to count the microstates. But if there is a temperature, it's hard to do that because you are in the canonical ensemble, and you will need to go to the microcanonical ensemble to count the microstates. But when the temperature is 0, it makes more sense because basically it's just a matter of counting ground states. So you have a system that is not thermally excited. You have some ground states and you want to count them. So it's a better defined and easier problem, and this will be important for us when we go ahead in our discussions. In the last few minutes, I would like to make a few more considerations on this black hole thermodynamics, and then tomorrow we will see that this temperature that seems just a formal temperature is actually physical. But let me make some other comments. Unless there are questions about what I just discussed. Well, this I can be very quick because I already commented on that. So if we reinstore the physical units, then we are led to conclude that the area cannot be directly the entropy. We need to add the Planck length squared, and this alpha is the unknown coefficient that will be fixed by 4 tomorrow. For now, it's an unknown coefficient. And since LP squared is G H bar over C cube, then you introduce an H bar there by hand. And the same is for the temperature. Also, the temperature a priori in general relativity it does not contain any H bar. But since you have decided that the entropy must be related to the area in this way, the temperature must be related to the surface gravity with a Planck length squared at the numerator. But then it also contains some factors C and G, so that you end up with this expression. So we saw here that is alpha kappa over 8 pi. I'm just reintroducing the physical units here. So I have alpha kappa over 8 pi. Since I multiplied this by the Boltzmann constant here, I have 1 over the Boltzmann constant, which makes sense because kappa t is some energy. And then the other units come out from the fact that here I have LP squared. I should actually write this relation with the physical units so that you see exactly how it arises. So it's this comes from comparing T ds to C squared over 8 pi G kappa dA. So I've introduced these physical units here. And then when I multiply the area by kappa over LP squared, I have to multiply the temperature, the surface gravity by the inverse. And taking into account these factors here, I obtain this. So this is what we have if we reintroduce the physical units. So just for the last time, I emphasize again that H bar is introduced in the temperature and in the entropy, just in this way. And this is, however, something inspiring, because, as I said, in order to account for the microstates, maybe we have to do some quantum mechanical considerations, but also to account for the temperature, we need to do some quantum mechanical computation. Because, as I said, the laws of black hole mechanics make sense in general relativity. In principle, there is a formal analogy with thermodynamics, but this is a formal thing. Again, in GR, black holes don't emit any radiation, they are at absolute zero. in GR because they don't emit. So they don't really have a temperature. But now we have seen that the temperature is proportional to h bar. So it makes sense that in the classical limit it goes to 0. It must arise from some quantum computation. This is what Hawking did. He did some QFT in curved space computation that certainly has an h bar and found that there is a physical temperature, not just a formal one. But this will come tomorrow. So for the remaining 5 minutes or so, I'll just want to make some estimates, some numbers, stick some numbers in, associate some numbers to these quantities, just to see how big, how small they are. So the fact that in the expression for the entropy we have 1 over the Planck length squared, the Planck length is 10 to the minus 35 meters, makes the entropy huge, right? Measured in units of the constant, Boltzmann constant, it has 10 to the 70 coming from the 1 over LP squared. So let's be more precise. If I take a solar mass black hole, has a Schwarzschild radius that is, do you know how roughly it can be? You can do the computation, but someone said something like 3 kilometers, right? It is correct. Something like this. The Planck length is this 1.6 10 to the minus 35. So there is a huge factor that comes out. So then you have that the area over LP squared is roughly. So from this, okay, let me not compute the area from RS, is the area of the sphere. Anyway, you get something like 4 times 10 to the 77. Which is huge. And it is actually 20 order of magnitudes more than the thermodynamic entropy of the sun. So this shows that the entropy of the black hole is something more than just the thermodynamic entropy of the body that forms it. So this may come from, this solar mass black hole may come from the collapse of the star, of the sun, but its entropy is much larger than the one of the sun. It's 20 order of magnitudes more. So it's not the thermodynamic entropy of the sun, it's something else. If we take a black hole of mass 10 to the 6 the solar masses, then we have an enhancement. Again, the radius is proportional to the mass, so we have 10 to the 12 more. So the entropy, A over LP squared, is 10 to the 90 roughly, measured in units of the Boltzmann's constant. So this exceeds the thermodynamic entropy of the universe. So it would be somehow thermodynamically favorable to throw matter into black holes because it increases the entropy much more than having matter outside black holes. So someone says that we are in a very particular, the universe is in a very particular state because it's a very low entropy state. I could increase the entropy by throwing the mass into the black hole. So we are in a very particular low entropy state. Okay, this is just a comment. And similarly, since I have h bar here, we will see this maybe tomorrow. The temperature, we should expect the temperature is typically very, very small. So typically for a stellar mass black hole, the temperature is overcome by the thermal radiation in the universe. So it's much less than 3 Kelvin. So I guess for today, I don't want to start a new chapter that is QFT in curved space-time and Hawking radiation. So tomorrow we will spend some time and do some justice to the Hawking's computation. It's a long and involved computation. We don't need to explore it in full detail, but I would like to present a baby version of that in 2 dimensions, but go through it more or less completely, so that at least for those that have never seen this, you see how it arises. There is a much easier trick that is the Euclidean trick. We will also see that later on, but let's keep the easy part for later. So tomorrow we will do that, and in order to do that, I will have to introduce some notions of quantum field theory in curved space-time, because one has to realize that in this computation that makes the entropy, the temperature appear, the back reaction of this radiation on the matrix is negligible, so we can consider the Schwarzschild matrix fixed and just do quantum field theory on a fixed background. We are not quantizing gravity. We are just considering quantum field theory in a curved background, but it's slightly different than quantum field theory in flat space. Some intuition doesn't work, and so we will have to introduce a little bit of machinery. So we will do this tomorrow. Okay.